Alrighty, everybody. So now let's revise ozone. Ozone is an allotropic form of oxygen and it can be prepared by the silent electric discharge of oxygen. You take a slow dry stream of oxygen and you perform a silent electric discharge and you get ozone. So if you're wondering why a silent electric discharge is needed, let me explain. This reaction from O2 to O3 is endothermic. So that already means that it's not leaning towards a very spontaneous type of reaction, but on top of that, the overall entropy of this reaction is also going to be less than 0. This means both these factors are not contributing towards a spontaneous reaction. So to prevent the reaction from going back, to prevent the decomposition of O3, we take a silent electric discharge. You get a 10% pure ozone, but if you want a much purer form, you need to take a battery of ozonizers. The properties include it's a pale blue gas, a deep blue liquid, and a violet black solid. So the color intensifies as you go from gas to liquid to solid. It has a characteristic odor, and in small concentrations it's fine to inhale, but if the concentration exceeds 100 parts per million, then you can experience symptoms like nausea, difficulty in breathing, etc. Now, when O3 becomes O2, so basically you're liberating a nascent oxygen atom here. This reverse reaction was endothermic, so this reaction is going to be exothermic. And on top of that, it's going to be very spontaneous because even delta S is going to be greater than 0 now. That makes O3 a very powerful oxidizing agent, but also easily explosive because of how spontaneous it is for it to decompose. Now PbS, when it reacts with O3, it gets oxidized to PbSO4. I- gets oxidized to I2. The quantitative method for estimation of O3, so you take PbI and then you buffer it against a borate buffer of pH 9.2. Iodine is liberated and that can be titrated against a standard solution of sodium thiosulfate. This is used as a quantitative method of measure of O3. Now, nitrogen oxides, so basically nitrogen oxides can easily and spontaneously combine with O3. This means that when planes travel, they release exhaust gases. These exhaust gases contain nitrogen oxides. These exhaust gases are combining with ozone that's present in our ozone layer, and that is causing the decomposition of that ozone layer. Along with freons are basically present in aerosol sprays or in our refrigerator gases as well. Now this is O3's structure. It has a resonant structure, you know that. The bond length is 128 picometers and the bond angle is 117 degrees.